In this video, we'll look at how to use combustion information from a carbon-hydrogen combustion analysis to determine the empirical formula of a compound. A reminder that an empirical formula shows us the simplest ratio of the atoms in the compound. And a second reminder that combustion is the reaction of oxygen to produce common oxides. And so when you have a carbon and hydrogen containing compound, your oxides will be CO2 and H2O. So we'll use this to find the empirical formula of organic compounds that contain carbon and hydrogen. We'll also have other information where we can determine the empirical formula when there's oxygen in a compound or other elements like nitrogen or sulfur or halogens. The most basic type is one where you have carbon and hydrogen. And in order to be able to do these problems, you need to be confident with solving empirical formulas from mass data or from percentage by mass data, because some of the math that we do is learned from that type. So in this kind of a combustion, what we are doing is we're going to burn the carbon-containing compound by adding an excess of oxygen. And the products are collected in these tubes here. So we've got our first tube that will collect our water and the second tube that will collect our carbon dioxide. And when you put in the tube is a compound that absorbs water really well, like an anhydrous salt. You'll learn about hydrates a little bit later, or you may know about them. So you want something that's going to absorb the water that passes through. So for example, if you started with something that was 7 grams and during the experiment the mass went up and went to 8 grams, you would know that the mass of water that you had absorbed was 1 gram. Similarly, in the second tube, you have something that absorbs the carbon dioxide really well. So for example, it might be a calcium oxide that absorbs the carbon dioxide to produce the carbonate. What we'll do is look at an example. So in this example, we have a 1 gram sample of a compound that contains carbon and hydrogen only. So we sometimes think of that as CXHY. Your variables can be different if you want them to be. We're combusting it, so we're reacting it with oxygen to produce CO2 and H2O. We know our starting mass of our sample, and we know the mass of the carbon dioxide that's produced and the mass of the water that's produced from the question. Now, the key idea here is that we really want to know about this compound on the left-hand side. We want to know how many moles of carbon are in there and how many moles of hydrogen are in there so that we can determine the empirical formula or the simplest ratio. The information that we have is about the carbon dioxide and the water, and so the idea here is that all the carbon from here has landed in the CO2. So I can use the carbon dioxide to help me to determine the amount of carbon, and all of the hydrogen from here has ended up in the water. So that's the information I'm going to use. So first, we'll use the information from the CO2 to figure out how much carbon we have. And we need to work in moles, because if I know how many moles of carbon dioxide I have, I can figure out how many moles of carbon there are in that compound. A reminder that the moles is equal to mass divided by molar mass. And for these problems, kind of having a side calculation done of the molar mass of water and carbon dioxide is helpful. The molar mass of carbon dioxide is 44.01, okay, which we calculated from carbon, which is 12.01, and 2 of oxygen, which are 16 each. So I find that the moles of CO2 is 0.075846. Now what I really want though is I want the moles of carbon. And because for every 1 CO2, there's 1 carbon atom, that means that the number of moles of carbon is going to equal the number of moles of CO2. So my moles of CO2 is going to be the same. Similarly, I'm going to use the water to determine the moles of the hydrogen. So the moles of the hydrogen, I have 0.6919 grams. The molar mass of water is 18.01. So my moles of water is 0.038396. Now for the water, I'm going to use that to figure out how many moles of hydrogen were in the original compound. The moles of hydrogen, though, is going to equal to the moles of water times 2, because in one molecule of water, there are 2 hydrogen atoms, so there's twice as much. So my moles of hydrogen in this case is 0.076792. Now it gives us a step 3 here, which we'll use in other problems when there is oxygen. Our compound that we're studying, as the question suggests, contains only carbon and hydrogen, so we don't need to do this step. To find the empirical formula, I need to find the simplest whole number ratio. At the moment, I do have a mole ratio, but it's not in a whole number form, and this is just a different style of setting it up. In the previous examples, we set up a little table, which you can do. It's the same concept. We've got this ratio between the atoms, and we want to simplify it to a whole number ratio. And I do that by dividing by the smallest number of moles. In this case, the moles of the the moles of the carbon, and what we end up with is a 1-to-1 ratio. And this, even though these numbers look kind of close to each other, it's a good idea just to throw them in your calculator and just make sure, unless you're really, really good at mental math, and you want to make sure that it rounds pretty much to 1. And you'll also notice that throughout that problem I carried lots of significant digits, and the reason for that is to make sure that when I do this last step, I get nice whole numbers. Okay, now for this one, I'm not going to go through step 1 and step 2 in the same slow manner. Okay, I'm going to kind of talk through and give the final answers. You should try it on your own. Okay, the amount of carbon dioxide is going to come from the CO2, and the amount of the hydrogen is going to come from the water. Okay, so in this compound we have carbon, hydrogen, and oxygen. We're making CO2 and H2O. We have a 0.684 gram sample, and the CO2 is 1.312 grams, and the water is 0.805 grams. So to find the moles of the carbon, I found the moles of the carbon dioxide first, and the moles of the carbon is the same as that. Okay, so I took my 1.312 and I divided by the molar mass of carbon dioxide, which is 44.01, and I get 0.029811. Lots of significant digits. For this one here, I'll show you the 2 steps. So I found the moles of the water first, which was 0.044673. I found that by dividing the mass of the water divided by the molar mass of the water, which is 18.02, and that gives me my moles of water. Now, because the moles of hydrogen is 2 times that, I need to double this number to get the moles of the hydrogen. Okay, so this is the moles of C, this is the moles of H. I'm going to write it clearly so that I can see it in future steps. Now, I was able to figure out the carbon directly from the carbon dioxide because all the carbon went into this compound, all the hydrogen went into this compound. For the oxygen, its location is not really known, so I can't really say that all of this oxygen is from the compound, because remember, we also found the we also added a lot of oxygen to this. Okay, so we could figure out this oxygen and then kind of work backwards through to figure out the total oxygen over here. But because we have the mass of the original compound, the simplest way to figure out the oxygen is to look at the fact that the mass of the compound is going to equal the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen in that compound. So I've got the mass of the compound, I've got the moles of carbon, so I can figure out the mass of carbon. I've got the moles of hydrogen, so I can figure out the mass of hydrogen. So I'll be able to solve for the mass of oxygen. Okay, so over here, I'm just going to show the mass of carbon separately. The mass of carbon is going to be the moles of carbon times its molar mass, okay, which is going to equal 0.35803 grams. Okay, we know how many moles of carbon are in this compound, so we can figure out how many grams of carbon are in that compound. Similarly, for the mass of the hydrogen, I know how many moles of hydrogen are in that compound, so I can figure out how many grams of hydrogen simply by multiplying by its molar mass. This is just the mass of just H, so I just multiply by the molar mass of H to get my moles of my grams of 0.090238. So now I've got my mass of my carbon, my mass of my hydrogen, so my mass of my oxygen is going to equal my mass of my compound minus my mass of my carbon minus my mass of my hydrogen and so my mass of my oxygen is 0.23573. Just carrying again, lots of significant digits, so that when I get to that final step, I get some nice whole numbers. So my mass of my oxygen is there, but to do my empirical formula or determine my empirical formula, I need the moles of oxygen. So I'm going to divide it by the molar mass of oxygen, which is 16. So my moles of oxygen is 0.014733. Okay. So then in my last step, I want to find the mole ratio. So I'll show you another kind of setup. You can do the same setup we did before, but you can also think about it how we did in our previous lesson. We've got carbon, hydrogen, and oxygen. Our moles of carbon is 0.029811. Our moles of hydrogen is 0.089452, and our moles of oxygen. To find the ratio, I'm dividing by the smallest one. So I'm dividing all of these by the moles of oxygen, or the 0.0147332. That puts it into a 1 to something ratio, right? So in this case, it puts it in a 1 to 2 to 6 ratio. Therefore, my empirical formula is C2H6O. These do require lots of practice, right? And there are some different styles of questions that have other elements like nitrogen or chlorine, and you have other information that will help you to solve for those elements in those cases.